Specifically, what we're going to be covering in part one today is, as you see on the slide, why we built transactions, their design goals, their use cases. We'll dive into the transaction sessions and syntax and provide you with some code samples. So all of the key things you need to know to get started with these. Today's session is actually being recorded. You'll receive a replay within the next couple of days. And from that, you'll be able to go back and listen to any parts that you may have missed first time around, or share it with colleagues who may be interested. And also, by registering for today's webinar, you're automatically enrolled for part 2 in this series in 2 weeks' time. And that's going to give a deeper dive into the tips and tricks that help you get the most out of transactions. So even before we added multi-document transactions to MongoDB back in 2018, we've already seen very strong adoption across pretty much every industry and most operational use cases, from highly transactional applications in traditional banking, through to cryptocurrency, through to e-commerce, as well as use cases like IoT and AI. And that's because MongoDB has always supported ACID transactions, and those were scoped to the level of a single document. Now, single document atomicity is sufficient, we estimate from our experience, for about 80% of use cases. And that's because the document model allows you to collapse otherwise separate parent-child tables that you would have in a relational model to a single document. So let's dig into that concept a little bit more. So different databases take very different approaches to data modeling very clearly. So here we've got a simple customer object, which is modeled in a relational database across 7 separate tables. It includes customer name and date of birth, and then multiple tables to store things like address data, contact details, interests, and so forth. And so if we need to update that, let's say our customer contact moves to a new job, we need to update multiple tables, the customer table itself, their address, their phone number, and we need to do that in a multi-record transaction that spans multiple tables in an all or nothing operation. So that gives us ACID guarantees to enforce data integrity. However, document databases are different because we're able to collapse what were those separate tables into a single rich document structure, where child tables are actually embedded as subdocuments and arrays into that single document structure. So in that case, when we have to update any part of that customer record, all of those details are updated in a set of operations that constitute a single transaction against a single document. So that gives us the same kind of transactional guarantees as relational databases. So in that sense, one or more fields can be written in a single operation that includes updates to multiple subdocuments and even the individual elements of an array. You get complete isolation as that document is updated. So none of the document updates are visible to other threads until the write's committed. And any errors will cause that operation to roll back so that clients receive a consistent view of the database. And all of that's handled within MongoDB itself. It's all handled within the database. So the developer doesn't need to do anything on the application side to enable that. And so, as I said, for many apps, single document transactions meet the majority of data integrity needs. So with that said, why have we spent kind of 4 years and tens of millions of dollars in building support for multi-document transactions? Well, there are really 3 reasons. The first is that there are some apps that require them, and it now gets even easier because you have multi-document transactions available to you. MongoDB has always been focused on enabling developers to build highly resilient, highly scalable applications very, very quickly, and this just makes it easier. Before the delivery of multi-document transactions, you could build them back in code, but that's kind of a lot of work. So we have a very large financial services customer who had been doing exactly that. They built transactions back in their application. And simply by moving to multi-document transactions in MongoDB, once we released that, they were able to remove over 1,000 lines of code from one of their trading apps. So, it removed a whole bunch of complexity and ongoing maintenance of that code. Second reason, it's future-proof. So should you require them in the future, you may not require them today, but should you require them in the future, they're there. And thirdly, there are some classes of applications where multi-document transactions are expected, even if the app is actually not going to use them. And this is because we've seen developers and DBAs who have been conditioned by 3 or 4 decades of relational modeling, data modeling, to assume that any database that doesn't support multi-record or multi-document transactions is purely suitable only for a niche set of use cases. So that objection essentially is entirely cleared away. When we set out on the path to transactions, we had some key design goals. So firstly was to make them just like relational transactions. So they're multi-statement, they use a very familiar relational syntax, things like start transaction, commit transaction, abort transaction. So they're very familiar to anybody coming from a relational background. They're easy to add to any application. They're fully conversational from the drivers. They're not some kind of weird stored procedure. They operate across multiple documents in one or many collections and databases. And there's no difference, you know, however your cluster is configured, whether it's configured as a replica set or across a sharded cluster, there is no difference in the syntax and the API that you use to commit transactions. And Ali will demonstrate more of that in a little while. In terms of asset guarantees, they provide the kind of very, you know, strong data integrity you would expect. It's snapshot isolation with all or nothing execution, and there's no performance impact to the database as a whole. So we've added and evolved MongoDB a lot to be able to add this capability, to support this capability, but that hasn't then added overhead to other operations in the database. So MongoDB is as fast, in fact, it's faster than anything we've had before. So with all of that said, we're now going to go into how we've implemented transactions and how you can use them with some code samples, and we'll look at the API. So I'm going to pass across to Ali to take this part of the talk. Ali, across to you.
Thank you, Matt. So as Matt mentioned earlier, one of the motivations for implementing transactions in MongoDB, or multi-document transactions in MongoDB, is making developers' lives easier. And part of that, in that vein, we wanted to make this as expected or familiar as possible to developers. So this is how you open a transaction in MongoDB. First, you start a session. Then on that session, here I'm calling it S, I start a transaction on that session. Now, next what I'm doing is I'm inserting 2 documents and passing in that session. And then, of course, if those inserts are successful, I go ahead and commit the transaction, otherwise abort if an exception is raised. So this is the simple syntax that we expect from any system where we're leveraging transactions. So it's conversational, it's simple, and it's idiomatic to the programming languages. All right. So next we have, we're going to walk through several guarantees transactions give you that you can rely on. So as Matt mentioned, we have snapshot isolation with transactions. Now I want to dig into more of what that means universally. So starting in MongoDB 3.6, we've introduced a global logical clock that keeps track of a hybrid logical time across the system. Now, don't worry if you're not familiar with what a hybrid logical time is. If you are interested, you can read one of the most cited papers in distributed systems, the Leslie Lamport paper around the Lamport clock. That's really what we've designed this system around. But for all intents and purposes for this conversation, let's think of this as an incremental value, and the increment goes on every time we accept a modification in the database. So here, let's say that I have a write that happens at time 100, and then as soon as another write happens, I increment time to 101, and then another write comes in, I'll increment to 102. It doesn't matter what the physical time between those writes are. I only am incrementing logical time when the modifications are accepted into the system. So if we think of the system this way, and I have a write coming in at 100, 101, 102, if I take a snapshot at that logical time 102, it only reflects the previous writes. So I'm going to see write 100, I'm going to see write 101, and write 102. However, if subsequent writes come in, like write 103, 104, 105, those are not going to be reflected in the 102 snapshot. And transactions keep the same snapshot throughout the duration of the transaction. So let's say in the extreme case, I have a transaction running for several minutes. Well, that snapshot is going to get staler and staler over time. Now, this is, of course, standard with snapshot isolation across any system, but something important to keep in mind as we go forward. So again, just to reiterate the point, if I have a snapshot at time 108, I'm going to see all of the previous writes from that time, and then none of the subsequent writes until I have another snapshot that's at a later time. So snapshot 108 will not see the writes happening later. Great. Let's move on. Additionally, another guarantee we spent a lot of time on providing our end users is the read your own rights guarantee in transactions. So here, I have a transaction that has performed an uncommitted right to this document. So let's say I am moving from street 94th Street to this 92nd Street. It's a big move in New York, but let's say that I'm moving those 2 blocks. Now, when we have this uncommitted right, if I have a separate read operation come in, outside of the transaction context, it will read the previous committed value. It's not going to read the uncommitted rights until the transaction has committed. However, if the transaction writes to that document and then does a subsequent read from that document, this means that it will see its own uncommitted rights. So this is actually a guarantee that we expect in other systems. And the transaction has access to read its own uncommitted rights that it's performed. No other operation will read uncommitted rights. And the level here that we were talking about, the isolation level, is snapshot isolation from the previous. So this is a separate guarantee that we give with our transactions. Great. So perfect. The next one is all or nothing execution. So let's say I do 2 rights or 3 rights across 3 documents. So I'm updating these 3 documents in my transaction, but I have not yet committed the transaction. Now, as soon as I go on to commit the transaction, all of these uncommitted rights will be committed together, or they will be rolled back if one of them has an error, let's say. And all of this is just all or nothing execution and illustrating that. Great. Next, I just wanted to show how familiar this syntax is in the wild. So we actually have an example MySQL transaction on the side of the MongoDB syntax here. So it does look very familiar. One thing I do want to note that you guys should keep in mind if you're writing transactions yourself is to make sure to pass the session object into the CRUD operations you want to execute within the transaction context. If you do not pass in that session object to the insert one or update one here as listed, it's not going to be executed as a part of the transaction, and you might see anomalous behavior because you're not actually leveraging a transaction. So make sure to pass that session in. But of course, errors happen in the system. So how do you handle errors if they arise? Now, I'm going to walk through actually what you had to do in MongoDB 4.0, but now with MongoDB 4.2, we've simplified this dramatically. And I'm really excited to kind of share that with you. So first, we just have an example transaction here. I'm inserting across 2 collections and yeah, doing 2 inserts across 2 collections. Great. Now let's go into first type of errors that we want to recover from. Now, we've introduced this concept of error labels, and you can manually go in and listen to this error label called transient transaction error. Now, an example of a transient transaction error is an error such that if I were to retry the transaction from the top, I could result in a successful transaction. So an example of this would be a network error, a write conflict, something where I could try again and it could lead to success. However, an anti-example here would be something like a parsing error, right? If you use the wrong syntax for the MongoDB API, that means if you run that transaction again, you're going to get the same error, you're going to get the same result. That is not a transient transaction error. So here, we want to listen to errors like network errors, and then retry from the top. And this is a way we would do that. You just listen for the error label, transient transaction error, and then go ahead and return to the loop where you're trying to commit the transaction. Great. But what happens if we get a network error on the commit itself? So let's say that I've done my 2 inserts, and now I send the commit command, and I get a network error as a response. Well, that can mean 2 things. Either I got a network error on the trip to MongoDB and on the trip to the server, and that would mean of course, my transaction didn't commit because I didn't even reach the server. Or it could mean that I got a network error on the trip back from the server, meaning that MongoDB got my request, it committed the transaction, but I just didn't get notified because the network dropped or blipped on the way back. So those are kind of two different extreme cases for what might happen on a network error on commit. And this is true for any system. But it's surprising how little we think about these problems in the wild, even though it can dramatically leave the application in an indeterministic state. So what we wanted to do at MongoDB was provide a second error label for this case. So if we move on to the next slide, I show an example here. So this is the error label called unknown transaction commit result. And what the unknown transaction commit result is, the error label means is like if I get a network error, if I get a write concern error on that commit where I'm leaving left with an indeterministic state of whether the transaction actually committed or not, what I can do is listen for this error label and then keep sending the same commit message to the primary. And if the primary, like let's say I have an election and there's a new primary, well, the new primary will just respond to that commit message eventually with whether the transaction committed or failed. So we keep a history of the last transactions per session state on a transaction side table, so we can go ahead and check that reference and then just recover the end result. So you're never left with an indeterministic result. You can always get to a deterministic answer of whether the transaction committed on a network error. Great, so that was the value of that second. Now here's what it is putting it together. And as far as I'm concerned, this is really, really close to production worthy code, and I'm really proud to be able to put that all in one slide. So here we have combined the notion of retrying on an unknown transaction commit result and the transient transaction error label. So what we're doing is if we get an error on commit, we're listening for those errors. And if it has an error label, we're still trying to go and send the commit message. Now, if we get an error on any of the other statements before the commit that has the transient transaction error label, we'll just start the transaction from the top. So that's what this is doing. Great. Now, given everything we talked about in 4.0, you still have the flexibility to listen to those error labels yourself, but we made this even easier in 4.2. So here's an example of what you need to do error logic and to handle error logic in MongoDB 4.2. So we talked about how I was proud of all that code on that one slide in the previous slide, but now I'm even prouder of us, right, as an engineering team. So here's what it looks like. We've introduced this new command called with transaction. And what it does is it automatically does that retry logic for you in line with MongoDB's best practices. So now if you're using the with transaction, you don't need to listen for the error labels of unknown commit results or transient transaction error label. We do that for you. Now, with this logic, we're retrying up to 2 minutes. So that's a non-configurable value. We have future plans to kind of extend that and allow you to specify a client-side universal timeout. But right now, it's really around, it's the 2 minutes for retrying is not configurable. Great. All right. So now, because we've talked about what we've done so far is we talked about guarantees with transactions, retrying transactions. Now we're going to talk about write conflict behavior and locking in MongoDB. So here we have a transaction. We have 2 transactions. We have the orange transaction and the pink transaction. Now, what we're representing is the second transaction here. It's going to perform the write on this document. Let's say they were both sent in parallel, but the pink transaction happened to get in first, this transaction 2. Well, transaction 2 was the one that required the modifier, acquired the modifier lock on the document. And what that means is if I have an uncommitted write on a document, that means that no other modifiers can come in while I'm holding that uncommitted right on the document. So here, the first transaction, because it wasn't able to obtain the lock, would abort with a right conflict. Now, this is to proactively prevent deadlocks from happening in the system. It's also why right conflicts are considered a transient transaction error in MongoDB. That is because they should, if you have a contentious document with many concurrent writes happening on the same document, that could lead to right conflicts, and we should be prepared to retry them client side if you get those errors. Great. So now what happens for operations that come into the system outside of the transaction? So if you've used MongoDB before and you perform writes within the application, you've noticed that you don't get right conflicts in normal writes in MongoDB, right? Non-transactional writes in MongoDB. So if I have the same transaction come in, transaction 2, and it takes that lock on the document because it has uncommitted writes, if a second operation comes in, and this is a typical MongoDB write, and tries to modify this document, well, it's not going to be able to successfully obtain the lock. But instead of aborting the write operation and surfacing a write conflict error, which would be a breaking change or a big change across any application, instead the operation blocks behind the transaction committing and infinitely retries with backoff logic until max time MS is reached. And max time MS is that timeout that you can specify on the operation level. Great. Additionally, we have the WireTiger cache structure, and how it works with transactions is another interesting consideration to have in mind as you move forward with transactions in production. So here we have how we structurally represent data in MongoDB, but the most interesting piece is the update structure. So the update structure contains multiple versions of the document. Now, everything that we're storing in the data portion of the update structure is just the deltas of the changes at that given time. So we have the time, we have the transaction ID, and we have the data. Now, the reason why we have this update structure is so that our storage engine can represent different versions of the documents at different times. So if I have a document that, or a snapshot at time 102, which we discussed earlier, then I would need to service this document's version at that time 102, even if subsequent writes have happened in the system. So that update structure provides all of the context so that we can service different versions of the data, different versions of the document in line with the snapshot you're using. So, as you might imagine, if we have to keep a bunch of state around the history or the types of writes we're doing on these documents, that could build up cache pressure. And the cache pressure builds up by the write volume after the snapshot was created. So let's say I create a snapshot. Well, now I have to keep that update structure for every modification that comes into the system after that snapshot was created. And what I mean here by write volume is we talked about how in the update structure, we only store the deltas, the changes. So write volume here is really about how big the writes are and how many writes there are. So it's a factor of both of those things. Now, one thing to keep in mind, because transactions support snapshot isolation, transactions use the same snapshot throughout the duration of the transaction. So let's say that I open a transaction and grab a snapshot, right? Like grab a snapshot time. This is time 102. I hold on to that time, and every read I do within that transaction is served as if it was happening at the time 102. That means I have to be able to serve that version of the document, those reads at that version of the document until I can commit to the transaction and then release the locks and allow the snapshot to be cleaned up. So transactions use the snapshot throughout the duration of this transaction. We have to keep that history around, and that's how you build up that cache pressure. And the update structure can only be cleaned up after the snapshot is evicted, right? That's when we release those locks on the resources. Great. And then going, just to wrap up a little bit, going forward in part 2, we'll be digging more into the exact operational considerations to have, and also developer tips and tricks going forward. Passing back to Matt.
Great, thanks, Ali. So just to talk a little bit about the engineering efforts that have brought transactions to MongoDB. I mean, it's been a multi-year project, started way back in 2015 with the integration of the WireTiger storage engine. And we've worked on pretty much every part of the platform to make transactions a reality, from the storage layer itself through to replication and the consensus protocol we're using there, through to the sharding architecture. We've built out fine-grained consistency and durability guarantees into the database. Ali mentioned the introduction of the global logical clock based on some of the earlier prior art by Leslie Lamport. And we've actually written our own SIGMOD paper that goes into the implementation of that global logical clock for those of you who really want to get deep into this. And what we've done is we've exposed all of those enhancements through our API. So all of this is fully consumable by all of the supported MongoDB drivers. Our first release of transactions was last year in the MongoDB 4.0 release, and at that time, transactions were scoped to a replica set. And then in 4.2, which we announced in June of this year, and which went GA in August. So 4.2 is ready, it's production ready, you can use it for your production apps. That's where we brought distributed transactions which work across sharded clusters. And remember, there's no difference in the API, there's no difference in how you commit transactions across a replica set or a sharded cluster. Just to go into a little bit more of a timeline of the key engineering projects that have enabled multi-document transactions in MongoDB. I'm not going to go into all of these, but by building the necessary infrastructure to support those transactions, we've improved the database across the board in a number of critical areas that apply whether you use transactions or not. So, you know, for example, bringing WireTiger in as our storage engine, replacing the original Nmap storage engine, that was something we did back in 2015. And that instantly, not only does it provide a foundation for transactions today, but it also at that time brought around major scalability and performance enhancements by offering much finer grained consistency or much finer grained concurrency control. In a later release, we moved to the Raft consensus protocol for replica set elections. So that makes elections much faster, and much more deterministic. Through the introduction of that global logical clock, we can offer much more flexibility in tuning things like read and write guarantees across multiple nodes in the cluster. So these are things that benefit you whether you use transactions or not. But the key design goal of all of these projects is to, you know, deliver transactions in MongoDB, but to preserve and enhance our core properties of the platform. So to maintain the full power and flexibility of the document model and the advantages of distributed systems for things like resilience and scale out and workload isolation, and doing all of this without incurring any performance impact to the database itself. And we've been able to do that. In terms of looking at what has changed in the latest release of MongoDB Server, which is 4.2, which is available now, you can download it or you can run it as a fully managed, fully automated solution on MongoDB Atlas, which is our database as a service. We mentioned already distributed transactions, so that extends guarantees to sharded clusters, but there have been a number of other kind of really important enhancements that just simplify application development. The first is the delivery of large transactions. So by representing transactions across multiple oplog entries, you can now write more than 16 megabytes of data in that single ACID transaction. Now that's subject to an existing 60-second default runtime limit for your transaction. We'll talk much more about that in a couple of weeks' time in our deep dive. So what that means is you don't longer need to experiment to see whether you would hit that 16 megabyte limit, and that's especially useful for those use cases where you're atomically inserting multiple large documents in the database. So there's no storage limit or size limit on how large your transactions can be. We've exposed very deep transaction diagnostics by writing metrics to the Mongodb log. So you could look at things like execution time, locks, the number of documents that are touched. So this really helps developers to tune application performance. We've also enhanced the current op and the server status commands. So there are transaction-specific sections in those commands. So you can get instant insight into all of the running transactions in your database. And transaction error handling, Ali referenced this with some samples, but we've got new driver-side helpers with a callback API, which makes it much easier for you to develop retry logic in your app that handles any transaction abort. So a number of things that continue to build on the transactions foundations we laid in 4.0. They get even easier and more flexible to use in the latest 4.2 release. Now, we're not the only distributed database or so-called NoSQL database. We don't really like the term NoSQL, but people tend to use it anyway. We're not the only distributed database that offers multi-document transactions. There are some others, most of which have debuted fairly recently, but there are some big trade-offs. So here are the things that we believe you really need to look at when you're evaluating different distributed databases and their transactions capabilities. So the first is, does it apply transactions to both your base data in your collections and tables and to your indexes? Now that's important because many of these distributed databases have eventually consistent indexes which are updated asynchronously from the base data. So you can get different results depending on what you're querying, whether it's a base table or an index. And if a node crashes before that index is updated with that transactional update, you can get data loss. So you need to be very careful on that side. Secondly, you need to consider, does it enforce isolation and consistency server-side, or is it just some kind of client-side implementation where you actually have to avoid modifying any documents that are part of, that are also being worked on by a transaction? So in those situations, non-transactional reads can actually fail to read changes made in a transaction even after the transaction commits. Some of the implementations you see are just stored procedures, which you have to write and store yourself on the server. So that makes stored procedures increasingly are regarded as an anti-pattern, especially in modern microservices development. So it makes maintenance a nightmare. You can't do any kind of ad hoc transactions on your data. Some force all reads to appear at the start of a transaction and then all writes a batch to the end. So you can't implement business logic within the transaction yourself. When you look at others, they're limited to just a single partition or to running within a single cloud region, for example. So they can give you the kind of global scale that MongoDB's distributed transactions give you. And some are only available in like one or two drivers rather than all of the drivers that you might potentially want to use. So here's some reactions from the market. We have thousands of users in MongoDB Atlas today using transactions. We have many customers who have moved either new workloads with transactions or updated existing workloads where they're implementing transactions themselves. We've got a very large enterprise data integration company who actually embed MongoDB into their solution, and they've used MongoDB for a few years. They needed to have transactional capabilities in their database or in their application, but of course MongoDB prior to 4.0 didn't offer multi-document transactions, so they implemented their own in code. And what they were doing is they were committing each write as part of that transaction. They were using a whole set of two-phase commits. They were then doing a majority write for each write operation within the transactions. They had to wait for that write to propagate to a majority of nodes to be persisted there before they could acknowledge success back to the application. That gave them the kind of durability guarantees that they needed, but it could be pretty slow. When they moved to multi-document transactions in MongoDB, where we handle all of that in the database, all of those write operations then have a single majority commit write at the end of the transaction. And so the fact you've only got one network round trip rather than multiple network round trips, they were able to improve their throughput by 50%, reduce their latency by 90%. So they got a huge performance boost as well as significantly simplifying their application code. But here are some other customers. Cisco, they're been a very large and loyal customer of MongoDB. They several years ago migrated their back-end e-commerce platform that handles over $45 billion worth of transactions per year from a traditional relational database to MongoDB, and they've embraced transactions pretty aggressively. As they say, no other database has the power of NoSQL and cross-collection ACID support. And a quote here from Steve O'Grady at RedMonk, who's been tracking databases for developers for many years. you know, and as he says, we, you know, with support for multi-document ACID transactions, MongoDB is built for customers to want to have their cake and eat it too, which is a pretty nice quote. If you want to learn more, obviously we're going to have a webinar in 2 weeks, which is going to go down into much deeper level into transactions and the best practices. But if you want to learn more about transactions generally and all of the other new features in MongoDB 4.2, which is our latest GA release, then you can register now for a free online course. Ali delivers one of the sessions. Asia, who's helping with Q&A today, delivers one of the sessions. So cover all of the kind of new capabilities in 4.2, from transactions to things like on-demand materialized views, through to very expressive updates we've implemented in the aggregation pipeline. There's a ton of new stuff in 4.2 that it's worth really taking a look at. So you can get all of that through the new online course. To get started with all of this, of course, you can download MongoDB yourself from the download center, pull it from one of our repos, and you can test it out on your own infrastructure. The easiest way, however, is to spin up a cluster on MongoDB Atlas, which is our fully managed global cloud service. And we are, through a special promo, offering $200 worth of free Atlas credits. So you can run a pretty meaty cluster for a while and test all of this out. All you do is enter the code MongoDB 4.2, and that $200 credit is instantly added to your account. We have, so all of these slides are going out later, so you'll be able to click on these links. We have extensive documentation on transactions in our manual. If you want to learn more about 4.2, there's a guide to what's new there. And I would encourage you to tune into the deep dive in 2 weeks' time to hear more about the best practices.